t is equal to 3 and t is equal to 5. And so I gave you a couple of practice problems where I asked you to interpret one of these integrals, and then I also gave you some practice problems on evaluating definite integrals. And so when we evaluate a definite integral, if we have the integral from a to b of f of x dx, then if we want to evaluate that integral and we want to come up with an exact value, then what we need to do is to find an antiderivative of the function in the middle, the integrand. So find an antiderivative, which is capital F, and evaluate that antiderivative first at the top boundary, and then at the bottom boundary, and subtract those two values. So the integral from a to b of little f of x dx is equal to big F of b minus big F of a. So antiderivative evaluated first at the top boundary, and then subtracting off antiderivative evaluated at the bottom boundary. All right, so these are the two main ideas that we talked about last time. Are there any questions on the practice problems out of section 5.3? Okay. All right, so Andrew, what questions do you have?
11.
Number 11?
I actually have two. I don't know if it's possible to do both, but 17 and 55b.
Okay. Anybody else have one that they would like to ask about? Okay, well, we'll start with these. So let's see, what do we have? We've got 11, 17, and 55b. This is all in section 5.3. Part B. Okay. So we'll start with number 11. We have the integral from -2 up to -1 of 4y cubed plus 2 over y cubed dy. And our job is to evaluate the integral. So, and this is what you asked about, correct?
Yes.
What were your thoughts?
What were my thoughts? I tried to figure out the antiderivative, and I got lost once I got to the 2 over y cubed.
Okay, so your issue has to do with this guy right here. So the first thing that I would do whenever I look at this problem right here, whenever I see 2 over a variable to a power, I'm going to rewrite this, kind of like we do when we do derivatives. So I'm going to rewrite this integral as the integral from -2 up to -1 of 4y cubed plus 2y to the -3rd dy. So once I do that, now I can apply the integral power rule for both of these. So to come up with my antiderivative, I'm going to add 1 to the power. So I get y to the 4th, and then I'm going to divide by that new power. So I get 4 over 4 in the front. And for my second term here, I'm going to add 1 to the power, so add 1 to -3, I get -2. And I'm going to divide by that new power. And then my notation that I'm going to use is I'm going to evaluate this antiderivative between -2 and -1. Are there any questions on finding either of these antiderivatives? So my life is going to be easier if I simplify this a little bit before plugging in my values. So here I can rewrite this as y to the 4th minus 1 over y squared, all between -2 and -1. And once I've simplified to a point that things look a little bit nicer, now I can plug in my boundaries. And so my top boundary is -1, so I have -1 to the 4th minus 1 over -1 squared. And then minus, plugging in the bottom boundary, so I have -2 to the 4th minus 1 over -2 squared. All right, now, one thing that you might be keep thinking about as we did this problem, I kind of cheated a little bit here. Because technically my antiderivative should have a plus c in here. Okay? So whenever I have this antiderivative, whenever I find an antiderivative, I really want to think to myself, oh, remember that plus c. However, when I'm talking about a definite integral, whenever I'm talking about an integral where I'm going to plug in these boundaries at the end, notice what happens. I'm going to include my little plus c's here, and I include a plus c here, and I include a plus c over here. And so when I do that, I've got a plus c minus c. Those c's are always going to cancel. So I tend to start to get lazy about including the plus c when I'm talking about evaluating these integrals.
Can we get lazy on the test as well?
Absolutely,
Okay.
yes. Yes. Now, when can you not get lazy? The answer is when you're asked to find a general antiderivative,
right.
Then you have to have the plus c on. But in terms of evaluating an integral, the theorem actually says any antiderivative will work. And so in particular, the antiderivative where c equals 0 is a nice one. Yeah. Good. Okay. Other questions so far? Okay, so now I'm essentially done now, except for maybe simplifying some numbers in here. So we've got -1 to the 4th is +1, minus 1 over 1, so -1. Minus 2 to the 4th is 16, minus 1/4. And so a little bit more arithmetic gives us 0. Minus 16 plus 1/4, and then I can combine those two numbers into one fraction if I want to, and if I don't, then I would leave it like that. Okay, questions or comments about that? By the way, the final answer here is a negative value once you -16 plus 1/4, and so that being negative tells us that more of the area, more of this function gives us area below the axis than area above the x-axis.
So the net is negative? Is that what you're
So
saying?
the net value is negative because -16 plus 1/4 is going to be a negative value. In particular, it's negative 15.75. So more area is below the x-axis than above. Okay, so our next one, number 17. We've got the integral from 1 to 9 of 1 over 2x dx. All right, so Erin, this was your question. What are your thoughts?
I broke it up into half times 1 over x.
Okay.
And then I took the antiderivative
Of
that, and I got 1/2 times natural log of x.
okay, good. So this is a good idea to sort of separate this into the constant times the thing that's changing. And so when I do that, there's actually a rule, and I neglected to write these down last time, but I will write them down today. But there's a property of integrals that the integral from a to b of c times f of x dx is the same thing as we can actually bring that constant in front of the integral, the same way that we could bring constants in front of a function and take the derivative of the function. We can bring that constant out front and take the antiderivative just of the function f of x. Okay, so we can really do that here. So I'm going to bring this 1/2 all the way to the front. And we have 1/2 times the integral from 1 to 9 of 1 over x dx. And so Erin's idea here of saying, okay, the antiderivative of 1 over x is natural log of x, and that's absolutely correct. However, you might not have thought that right away. Okay? Over here, when I had 1 over y, when I had 2 over y cubed, my recommendation was to immediately rewrite that as 2 times y to the negative 3. Okay? And I said, okay, we can do that, and then we can use the power rule. Okay? Over here, I did not immediately say, oh, let's rewrite 1 over x as x to the negative 1. And the reason for that is because this is the one exception to the power rule. So if I were to apply the power rule to this guy and say, okay, antiderivative of x to the negative 1 is add 1 to the power and then divide by the new power, well, I'm going to have a real problem because I'm dividing by 0. And so whenever I have this happen, I want to immediately say to myself, wait a second, that's the special rule. There's an exception here, and the exception is that the antiderivative of 1 over x is not using the power rule, but rather natural log of x. Okay, and technically it becomes the absolute value of x, so natural log of the absolute value of x, and that has to do with the domain issues of the problem. Okay, so once we have this, we can plug in our 9. So we have 1/2 times the absolute value, or I'm sorry, 1/2 times the natural log of 9 minus the natural log of 1. Natural log of 1 is 0. And so we've got 1/2 times the natural log of 9 as a final answer. Does that work for you?
Yeah.
So we wouldn't have to go log of 9 to the 1/2 and then log of 3?
So, I mean, if you could write this in other
just
formats. For example,
Would that equal the natural log of 3?
Yeah.
So when you have 1/2 times the natural log of 9, that's the same as natural log of 9 raised to 1/2. Bring that number in front up into the power, and now you have natural log of 3. So would you have to do that as part of the problem? No, but if you wanted to match the back of the book, you do.
That was where I got confused.
Yeah. Okay. All right. Other questions or comments about number 17? This is a totally legitimate final answer. 1/2 times the natural log of 9, and the book is clever and simplifies it more. Okay. So then how about we take a look at 55 part B. So we are given that the velocity is equal to 3t minus 5. And we're given a time interval where t is between 0 and 3. And in part B, we're asked to find the distance the particle has traveled during a given time interval. All right, so briefly in part A they asked the exact same question, but they replaced the word distance with displacement. So in part A, we're asking for the displacement of the particle. We're given the velocity, and so our displacement is going to be our integral from 0 to 3 of 3t minus 5 dt. And Erin, you said you had a question on part B, right? What did you come up with for part A?
Negative 1.5 meters.
Negative 1.5 meters. Okay. So if we evaluate this integral, we find the antiderivative, plug in the boundaries, we should end up with negative 1.5. And our units over here, t is in seconds, I believe, and the velocity is in probably meters per second. Okay, so what were your thoughts on part B?
I understood what they were asking, just not really how to get there.
Okay, great. So in this part A, so I'm going to go back to part A for this for a minute. So in this part A, if I draw a picture of 3t minus 5, let's see, we're going to hit the y-axis at negative 5, and we're going to have some sort of a line with a slope of 3, and our line will cross here at 5/3. And we are interested, and this is actually a bad drawing. What is 5/3? 5/3 is 1 and 2/3, which means that it's farther over than what I have drawn there. So let me try that again. Okay, that's a little better. All right, so this integral up here is calculating, first of all, we've got area below the x-axis, and then we have area above the x-axis. So in terms of this velocity function, this velocity function is saying that the velocity of the particle is negative from time 0 until time 5/3. So from time 0 until time 5/3, our particle is moving to the left. And at time 5/3, suddenly my particle turns and starts traveling to the right. And so this area down here is distance traveled to the right, to the left. If I turn the correct way. Distance traveled to the left. And then this area up here is distance traveled to the right. So our value up here is the net displacement. So we have distance left, distance right. Our distance right is smaller than our distance left, so we have a negative value. Our particle at time 0 is here, and at time 3 seconds is 1.5 units to the left. So that's displacement. Distance says, rather than saying net distance or net displacement, I'm saying how far am I going all the way to the left plus how far am I going back over. So algebraically what this looks like is that our distance traveled will be the integral from 0 to 3 of the absolute value of v of t dt. And so visually, when I draw this picture, originally my function looked something like this. But when I talk about the absolute value, what I want to do is take this triangle that's below the x-axis and flip it up above. And so my new picture is going to look something more along the lines of this. So how do I calculate those areas? I have a couple of choices. One is I can calculate both of these areas because they're triangles, and so I can do area of the base times the height times, so 1/2 base times the height, and then find this area and add it to this area. Or if I want to set up the integrals, then I can split this up into two separate integrals and say that for the first part, the integral from 0 to 3 of the absolute value of v of t dt is the integral from 0 up to 5/3 of not the original function v of t, but its reflection across the x-axis. So negative 3t minus 5. And then I can add that to the integral from 5/3 up to 3 of the original one, 3t minus 5 dt. So what I'm doing here is I'm taking this bottom triangle, and in order to calculate this area using an integral, I need to flip it up. Well, how do I flip it upside down? Well, I throw a negative sign in front of the function. And so now I'm going to get a positive area for this first triangle and a positive area for the second triangle, and I would add them together. Erin, does that answer your question?
Yes.
Okay, great. If I were to evaluate this, I would either have to pull that negative in front of the integral sign and then take the antiderivative, or distribute the negative sign through. So I would need to do something with these parentheses. Jeff, question? Or are you just stretching?
No. How did we get 5/3?
So how did we get that 5/3? So what I did is I asked myself, okay, my original function is y is equal to 3t
Oh,
minus
okay.
5.
I got it, okay.
Set it equal to 0 and solve for t.
All right.
All right, other questions? Okay. All right, so a few things to wrap up from last class before we move into section 5.4. We were talking about how to evaluate a definite integral. And I put the word definite in parentheses because technically we haven't talked about what an indefinite integral is yet. So we'll classify those differently, if not today, then on Tuesday. Okay, so one example that we looked at when we were looking at approximating integrals was the integral from 0 to pi of sine x dx. And we approximated this integral by looking at rectangles and drawing a picture of this function. So we drew a picture of y equals sine x. And we focused on the portion of y equals sine x that was along the interval from 0 to pi. And we took that particular interval, 0 to pi, broke it up into 4 rectangles, calculated the area of each of those rectangles, and added them up. And we came up with an approximate value. But now that we know how to evaluate these integrals, we can come up with an exact value. And so what I'm going to do is let's go ahead and do that calculation. The antiderivative of sine x, what is the antiderivative of sine x? So negative cosine x, right? Because the derivative of cosine is negative sine, so to get sine we need a negative cosine. So negative cosine x evaluated between 0 and pi. So that tells me that I'm now going to plug in my pi, so I've got negative cosine of pi minus negative cosine of 0. So here's where your trig has to come back to you, and cosine of pi is negative 1, so I have negative 1 minus negative cosine of 0. Cosine of 0 is 1. So in the end, we end up with, after sorting out all of those negative signs, we end up with a positive 2. So what that says is that the area under our sine function, starting at x equals 0 and ending at x equals pi, the area below the sine function and above the x-axis is exactly 2 square units. So what I'd like you to do right now is, at your seat, and maybe with your neighbor, I'd like you to evaluate the integral from pi to 2 pi of sine x dx.